They give us the potential to control the addition of functional groups. We can look for the synergic function between the groups. Look at the electrochemistry and the photochemistry. Now, in this really nice work from Anna Proust and her group, she looked at different types of linkers, and you could almost make out there that that's tin, siloxane, siloxane. And the point is that if you just look at the first reduction potential, the first redox process, notice that this cyclical thermogram is the opposite way around to the previous one I showed you. But notice that the first reduction process has shifted, well, to different positions for the different linkers. And the trend for that is that we have this first reduction potential goes most negative, it's tin, up to the most positive, which is phosphonate, which is the most electron withdrawing. And really nice things that people have done with these types of systems is, for example, this, which was Vincent Artero, Guillaume Izet, and Anna Proust. Again, they, for example, connected these iridium chromophores onto a polyoxometalate. They could irradiate the iridium. They could capture electrons from the iridium onto the polyoxometalate, and then they could reduce protons to form hydrogen. Not particularly efficiently, but it was a very, very nice proof of principle. So although we've kind of motored through it, we're kind of up to dig it to set the scene for what it is that we do. The reason I got involved in polyoxometalates, and it's a shame that Professor Mukherjee had to go, because I noticed that this ligand is almost exactly the same as his ligands. What we did, we took a pretty simple ligand, as you can see. It's just, we make this in situ. You add in the manganese, triethylamine, and methanol, and you can crystallize out this manganese-13 Hagen-like molecule really well. So if you see, I've taken off the organic ligands here, and you can see that the core of the manganese cluster is very, very similar to this, which is a kind of idealized alpha Hagen core. This, despite being manganese, not your standard tungsten system, keeps the nice redox chemistry. So in this case here, we have two oxidation processes, which are reversible, and then two reduction processes from the ground state. So we know from the crystallography that we start off with one manganese 4 in the center of our Hagen-like molecule to start with, and it's surrounded by manganese 3 polyhedra. As we then oxidize it, and we could isolate these by the addition of chemical oxidants, we could isolate the singly oxidized and the doubly oxidized molecules. Now, without going too deeply into this, from the magnetic perspective, it's really interesting. Because if you think about, if you have manganese 3, you're talking about 4 d electrons. You have manganese 4, you have 3 d electrons that you can use for magnetism. And what we found is that essentially the manganeses that oxidized were up in the top triangle or bottom triangle as we look at the molecule simplified. And they were having an overall, resulting in an overall hard axis, which means we can't get that doesn't lead to single molecular magnetism. We need an easy axis for magnetization. So because the easy axes of the manganese 3s in the top triangle, for example, are aligned along the edge of the triangle, what that results in is that perpendicular to that we have what we call a hard axis. Now, as we oxidize these, we lose the easy axes that these were giving us to start with, so the overall hard axis becomes less dominant. So despite having essentially fewer electrons as we oxidize it, despite removing 1 electron and 2 electrons, the point of this is simply that the magnet becomes a better magnet with fewer electrons as we essentially improve the anisotropy. Now, I'm really happy to talk more detail about that later, but I think there's no point going too much into that. But what this did for me was this really made me think that this kind of redox flexibility and the durability of structure was something really quite exciting, and it made me kind of inspired me to take this approach to polyoxometalates. So what we do in polyoxometalate terms is a pretty broad palette, but essentially we look at hybrid or phosphonate hybrid polyoxometalates, and we look at them from molecular up to nano, to softer materials, and so on, to structured solids. And so today I'll talk about a couple of stories that relate to this. The first one is visible light POM photoactivation. When I talked before very briefly about the use of POMs in organic oxidation reactions, that excellent work and the wide use of the polyoxometalate is typically excited around 300 nanometers or 330 nanometers, made me think that there's something that we can do. And these are the two systems that I think we can exploit for POM, visible light photochemistry, just purely talking about polyoxometalate. We first have what I'm going to call Endo charge separation. Really, that just means purely POM-based photochemistry, but moved into the visible region, where we excite the ligand to metal charge transfer, we go by the oxo radical, and we essentially oxidize our substrate and reduce our POM. That's how it already works. That is the decatungstate example I gave you before. We've also got this concept of exo charge separation, similar to what the guys did on the iridium system, where we have what I call the L, as some other chromophore, connected to a polyoxometalate, which we irradiate. We form a hole on the chromophore, an electron is transferred to the POM. We then essentially fill that hole on the chromophore to give us a stably reduced POM. So these look like they can do different kind of catalysis for us. We'll talk about both examples. Right, so first I'm going to start looking at this kind of like exo charge transfer. We made this family of different compounds here, so using tungsten 17, P2W17, connected by a phosphonate linker, we took terpyridine groups. We made a family of different ruthenium complexes. Different chain lengths to the polyoxometalate, different electron withdrawing and electron donating groups attached to the ruthenium. And we studied them for their photochemistries and their general properties. And I'll just, first of all, talk about this one. This reaction brilliantly crystallized. These systems don't always crystallize. These hybrid polyoxometalates, for those who work with them, probably know that they can be a bit of a nightmare to get a very pure crystalline sample of. But in this case here, we're able to get beautiful single crystals. One of the things I was really interested in general is the concept of some synergic function between the ruthenium chromophore and the polyoxometalate unit. So that's just noting for myself, really, 7 angstroms is our distance that we're going to look for things to happen within. This ruthenium polyoxometalate keeps our same electrochemistry that we expect from the polyoxometalate. If you look here, as we go towards the negative direction, you've got 1 electron, 2 electron, 3 electron on the POM, before we have this big peak here, which corresponds to the first of the organic groups being reduced, the 2 terpyridine groups. But then I have another POM reduction before the 5 pyridine is reduced. So brilliantly, like what I was talking about before, when I said we have this fingerprint to follow the redox chemistry of these things, we can do it again. So as we reduce the first process, we see the POM single reduction peaks growing in. Again, they follow. We have the second peaks. This I should mention as well, this is the ruthenium metal to ligand charge transfer band. We then continue, and we also have the first of our ligand reductions, so we see a shift around the ruthenium band. We have the shift again in the POM-IVCT. And again, a little shift in the POM and some more shift around the ruthenium. So that we were already very happy with this actually, because this was giving us our stable, electrochemically essentially reversible platform to look for some nice chemistries. Now the thing about the choice of ruthenium as our chromophore is it's not just an innocent chromophore. We can use it for different things as well. And if anyone has had a look at any CO2 reduction work, you'll know that this can do some nice CO2 reduction, this kind of ruthenium complex. So we looked at, again, the red cyclic voltammogram is under nitrogen. And in this case here, when we bubble CO2 into the system, you can see that we've got a very large peak happening here, which corresponds to the electrochemical reduction of CO2. From the GC, we've got our only gas-phase product was carbon monoxide, and that is broadly in keeping with the literature. Now this compound for CO2 reduction was first reported by Tom Meyer, and he found a very similar thing, and comparable turnover frequency in particular. But we're looking for synergy, or we're looking for, benefits of this hybrid system. So it's good, of course, it's good that it works, and then, we can do the catalysis of the individual components, I guess. But do we see any kind of benefit from the hybrid? What we did in this example was we added acid to the solution, to the cyclic voltammetry, the electrochemical solution. And when we bubbled CO2 through, we added different numbers of equivalents. Oh, actually, I've only got here 500 equivalents of acetic acid. When we did it with the control sample, so that's just the pure ruthenium complex, which was so just dissolved in acetonitrile and then bubbled with CO2. Acetic acid was added as well. We saw evolution of carbon monoxide, so a good turnover number of carbon monoxide, but of course we also saw the evolution of hydrogen. When we take the polyoxometalate, the hybrid system, we can add quite a lot of acid, and actually I've got newer data that I haven't added. This even goes far beyond this, and actually we can even further improve it. Here, at different potentials applied, we see essentially the CO2 conversion being maintained, although decreased somewhat on these data with the similar efficiency, but we see essentially no hydrogen involved. So this is really nice. So this shows us that we've got this, it's kind of a buffer, an in situ buffering process where we can add acid. And one of the big major challenges of CO2 conversion chemistry is to couple the protons. You can have proton-coupled electron transfer, then you can simplify, you can reduce the energy demand on your CO2 conversion chemistry. So actually, this work is ongoing, and we have. That's why we haven't published it for ages, because we're trying to get better data for it. So we've got it now. I think it's going to go in soon. Anyway, so we're starting to see this kind of synergy of function. The ruthenium control sample, just look at the complex on its own. If we irradiate the ruthenium, we excite the ruthenium, and we measure the emission, it comes in around about 760 nanometers. If we take the hybrid polyoxometalate, remember it's exactly the same ruthenium complex attached. In this case, the emission is quenched. So here again, we're seeing this kind of interplay between the two units. If we think about that in terms of energy levels, typically you excite your ruthenium, you excite the MLCT band up to the singlet state. You then have intersystem crossing to the triplet, and you have phosphorescence and emission as it returns to the ground state. In the case of the POM, we're adding in this extra energy level. And we're adding in this extra energy level because you can figure it out from the electrochemistry. We can figure out where the minimal energy is. So we know we're talking about around about minus 1.2 volts compared to the triplet, which is minus 1.6 according to the emission. What we have here, we don't see that emission, so we postulate that we have this charge separation between the ruthenium and the polyoxometalate. We then, of course, have charge recombination, and we reset to the ground state. To follow this kind of system, to follow this kind of process, you need to look at very short time scales. So we did some femtosecond transient absorption spectra. This on the left is the electrochemically generated. This is, you know, earlier on when I was talking about the fingerprint and so on, that is just one of those, but made into the same shape as one of these. And this red line here, is the absorption spectrum of the sample collected 3 picoseconds after excitation. So you can see that this band corresponding to the singly reduced polyoxometalate is there after 3 picoseconds, just matching up with this one. And then, as time goes on, it's relaxing back down to blank baseline. So what that means, that gives us a decay curve. We can get this decay curve, we can fit it with a double exponential, which ultimately gives us information on the lifetime of the charge separation and the charge recombination part. Yeah. And so what we find is that the lifetime of the charge separated state is around about 110 picoseconds, which, to be honest, is not very long. So when we were thinking about using this for catalysis, that number there, that 110 picoseconds, is very, very short. But we wanted to know if we could capture those electrons, we could make that electron transfer more than just, you know, charge separation. So we took, this is the blank sample, this is the hybrid POM before it's been irradiated, and then we started shining light on it in the presence of an electron donor. So we see the growth of the singly reduced polyoxometalate band as TEA is consumed to reduce the POM. We continue to irradiate, and we start to get up towards the second, but we never get there, even after 780 minutes. It's a very, very short-lived process. So we see that we have this function, we have this kind of synergy going on. We wanted to know if it was possible to repeat what the guys had done by the hydrogen evolution experiments. So we looked just from water. We added in just a little bit of water to an acetonitrile sample. We irradiated it, and hydrogen is evolved very slowly, very, very slowly. And it's, I think, basically the point of this is, while this system is nice and I think we can do things with it, this is perhaps not going to give us the kind of the excellent catalytic performance that we hoped for. But it means that we have to think about a different approach. So can we drive POM photocatalysis with visible light? Can we do this? Can we get to this thing over 400 nanometers? Our idea was a pretty simple idea, to be honest. Just take a polyoxometalate, so this is our tungsten 18, remove one, so then stick on a couple of phosphonate groups to that. In this case here, we've got electron withdrawing benzoic acids attached to the phosphonate linkers, as you can see here. And the concept was, can we do this with visible light? The initial signs were quite good. We did some calculations, and what I would say first of all about the numbers of these homolumal gaps is that the actual number of numbers are not exactly right. It's more a trend, is how my collaborator says we have to describe it. But we calculated for tungsten 18 using this kind of basis set and so on, and that matches up with literature approach. So this has got 2 phosphate groups at the center and 18 tungsten around it. And the homolumal gap that is calculated there is around about 2.26 eV. Now, when we connect on our organic groups here, the homolumal gap gets much, much smaller. But it's not that simple, is it? Because although the gap is much smaller, and therefore, in theory at least, there can be some absorption that is closer to visible region, a lot of that electron density is localized onto the organics. However, even in the HOMO, there's around about 20% located on the polyoxometalate core itself. what we looked at first was the electrochemistry of the three different systems. If we think about, remember, the 18, the 17, and then that hybrid. So we have our hybrids here. The main thing to look at here is where does the first reduction process happen. And for the blue system, it's around about 0 volts versus NHE. For tungsten 18, you can add on 400 millivolts to that, or negative. And for the tungsten 17, you can add another 100 millivolts, or negative. So the first sign is, I guess, pretty promising that our LUMO energy is much lower in our hybrid system. But what about the absorption? Absorption is one of the things that we're going to need to be working for us if we're going to make a good photocatalyst. Compound 1 is the benzoic acid hybrid. And you can see that compared to P2W17, which is the lacunary POM that we added the groups onto, you can see that the absorption in the visible is much greater. But quite interestingly, it's not actually very different to that.